Welcome. This is section 1.4, a review of trigonometric functions. So, trig review. So, we're going to take a look at some terminology, angles, radian, degree, measure, that kind of stuff. Definition of the trigonometric functions, evaluate, solve, and graph some trigonometric functions. So, just a quick review of what you should have brought with you from trig. All right, so first off, an angle. What is an angle? Well, first off, it has three parts. It has an initial side or initial ray, a terminal side or terminal ray, and a vertex, the point of intersection of those two. Okay? The reason we have a initial side and a terminal side is if we know where the angle starts, that's the initial side, and where the angle stops, that's the terminal side, we know the direction of measure. In this case, we go from the initial to the terminal, and this would indicate for this angle, because it is not in standard position, so that whole idea of clockwise and counterclockwise doesn't matter, that direction would be measuring a positive angle, or that is the angle that we want to measure. Okay? All right, an angle is said to be in standard position when its initial ray, that is the initial side, coincides with the positive x-axis. So over here is our positive x-axis, and so what we're looking at there is a standard position angle. Now, in a standard position angle, counterclockwise represents a positive angle measure, and if you had gone the other direction, that is clockwise, that would represent a negative angle measure. All right, so trigonometry. Trigonometry is based on angles and things that happen with angles, and then some geometry that comes into play here in a minute. But what is an angle? Well, an angle is that space between the initial side and the terminal side, the initial ray and the terminal ray. The vertex is that intersection point. So the vertex of a standard position angle then is the origin right there. That would be our vertex. Okay? It's really common to use theta to represent both an angle and its measurement, to represent an angle when it's an unknown value, or to define its measurement. Okay? We have a couple more pieces of terminology. What does it mean when an angle is called acute? Well, that means it measures between 0 and 90 degrees. Obtuse, if it's between 90 and 180. Okay? If it goes beyond 180, we don't have a fancy name for it that we use. There might be a name somewhere in history, but it's not one that's commonly used. Positive angles in standard position are measured counterclockwise, whereas negative angles are measured clockwise. That's just how that works. Don't ask reasons why for some of this stuff. It had to be decided, so this is just how it was decided. The entire system could work just fine if we measured everything the other way. It's just a matter of if we all do it the same way, it's much easier to keep things standardized. It's kind of like, why do we drive on the right-hand side of the road? Countries do it on the left and it works just fine. We just chose all to do it on the right, and as long as we all do it on the same side, on the right in this case, it'll work just fine. All right, so here's a picture of an angle measured positively at 315 degrees and negatively at 45 degrees. So there's our initial side right there because it coincides with the positive x-axis. This would be our terminal side here because it's the other side. And of course there's our vertex sitting at the origin. Okay? Two angles that have the same initial and same terminal are said to be coterminal angles. Same initial, same terminal, coterminal. Okay. All right. So when it comes to putting angles in standard position, it is not always a safe assumption to just assume that because you know the initial and because you know the terminal, you can measure the angle. To really know, you have to know how that was revolved. And what I'm saying by that is, what if the angle went all the way around and then a little more? There's no way to know that from just having a picture. So assume for a second that these weren't here. Well, I can't really scribble them out with a highlighter. That doesn't work. I'll scribble them out here. Okay? If we know that this is the initial side, and we know that this is the terminal side, how do we know, though, that the angle didn't do this and then stop there? And then when we measure that, it's going to measure differently than if we just went around one revolution. Okay? So in general, if theta is any angle, then theta plus n times 360 degrees, where n is a non-zero integer, will also be a coterminal angle. And not knowing the way that it's spun, there's a lot of different answers it could be. Right? So any angle that is bigger, any angle that measures larger than 360 degrees is one whose terminal ray has been revolved more than one full revolution. Okay. You can also form by going negative 360s too. Okay, so degrees. The problem is calculus does not like degrees, while there will be some problems where the final answer and the initial stem setup might be given to us in degrees. The work in calculus is done in radians. So we need to get out of degrees and get to radians. So what are radians? Well, radians are just a different unit of measure for the size of an angle. Just like if we're measuring the length, we could use something that makes sense, like the metric system, where everything is just tens of this and tens of that to get to the next larger unit of measure. Or we could use something silly like the household system, where we have, what do we have here? Well, we have 12 inches in a foot, and 3 feet in a yard, and 1,760 yards in a mile. But, oh, there's 5,280 feet in a mile, and don't even get me started about other weird measurements in that system. But it's kind of like that. You could measure an angle in degrees, or you can measure an angle in radians. Now, radian measurement is how calculus is done. So when we're working calculus problems, we need to make sure that the measurements we use are radian measures. Right? All right, so to design a radian measure to an angle, consider theta to be a central angle of a circle with radius 1. So pretend that for a second you're looking at a circle whose radius is 1. Here's a drawing of it over here. Okay? The arc length that is equal to the radius is exactly 1 radian in measure. So this would be, if this S arc length was equal to 1, then that angle theta would be exactly 1 radian, right? So what radians do is radians are a way to connect arc length on a circle with the radius of the circle. And what ends up happening is because we know from geometry that the formula for the circumference of a circle is 2 pi times the radius, what ends up happening is we get this nice little thing that happens that all the way around, the number of radians to make one complete revolution ends up being 2 pi. Okay, so if the radian measure is defined to be the length of the arc of the sector, but only on a circle of radius 1, so we're working with that unit circle. If the circle had a radius of 2, we'd have to have an arc length of 2 before we get to 1 radian. If the circle had a radius of 15, we need to have an arc length that had a measurement of 15 whatevers, feet, inches, miles, yards, until you had 1 radian. Okay? So what ends up happening is what we used to call 360, we're now going to call 2 pi, or the 360 degrees is equal to 2 pi radians. And then, of course, there's all those other conversions that come with that. If 360 is 2 pi, then 180 is pi, then 90 is pi over 2, 45 is pi over, what is that going to be, 4, 60 is pi over, 3, 30 is pi over 6, 15 is pi over 12, and then everything that goes with those guys. Okay? There is also a nice consequence, though, that the arc length of any circle is just the radius times the size of the angle that subtends that arc. How'd you like that for a fancy word? Right? Only works, though, when it's measured in radians. There are some that you just should know. If it's on this page, you shouldn't have to think about it to know it. Okay? So, find the radian measure for 60 degrees. Well, I should just know it, but let's pretend for a second that I didn't. And so how do I find the radian measure for 60 degrees? Well, I just simply set up a proportion. If pi radians is the same as 180 degrees, then how many radians would be equal to 60 degrees? And so I can just set up a proportion and solve. So crisscross multiply, you get 60 pi is equal to 180x. 60 pi divided by 180 is equal to x, and now these are going to be radians, right? I mean, they always have been, but when we simplify that down, we get pi over 3 is equal to x radians. So now, if you're watching what I just did and thinking, hey, that was great for finding this, you missed the point. Is there anything magical about 60 degrees that made this process work? Or is this the process for any? Right? All right, now there are some people who will say, oh, just memorize a formula. Because honestly, isn't there a formula hiding in there somewhere? Isn't there a formula hidden right here that x radians is equal to theta degrees times pi over 180? Isn't this step right here always going to be, if this was some angle theta, won't that always be that theta? And sure, you could memorize that, and that works too. Okay? Now, if I was going to simplify this process now, because this is the other direction, so what is 5 pi over 4 if we convert that to degrees? Okay? Well, 5 pi over 4 over x degrees is going to be equal to that pi over 180. And so we get pi x, or x pi, is equal to 180 times 5 pi divided by 4. If we clean up that right-hand side a little bit, so let's see what we can do here. I think we can do a simplification with the 4 and the 180, right? What's 180 divided by 4? And so we get x times pi, or pi x, is equal to 45 times 5. What's 45 times 5? Is that 215? I think. I believe so. And so then we get pi x, and we get the x then is equal to 215. No, not 215. 225, right? 225 degrees. Right? Now, if you're one of those people who likes to, I'm seeing a formula and memorize a formula, this step right here is your formula, right? Or maybe if we combine that step and this step, that would be our formula, that x degrees is always going to be equal to, let's see, that's my radians at the 5 pi over 4 multiplied by 180 over pi, and that would be your formula. Right? All right. Now, let's start bringing trigonometry into it, because we haven't done any trig yet. We've just looked at angles and ways to measure them. Now, depending on who your trigonometry teacher was and how they taught it, there are basically two different approaches to the study of trigonometry, two different ways that it's taught. In one way, everything is taught starting with triangles and doing right triangle trigonometry. In the other approach, everything is taught from a standard position angle terminal ray kind of approach. Now, ultimately, even if you are taught trig from right triangles, you always have to end up over there in that terminal ray points standard position angle business, because the limitation that exists in right triangle trigonometry is in right triangle trigonometry, this angle theta, oops, I don't want the arrow anymore. This angle theta that we're talking about here can never exceed 90 degrees. It can't even get to, beyond 90 degrees, because you can't have a right triangle with bigger than 90 degrees in it. It doesn't work that way. Okay? So all of this stuff down here about opposites and hypotenuse and opposites for the reciprocal functions and all that are useless unless you can draw it as a right triangle. Okay? Now, this approach over here, it's more common now than the right triangle trig. The right triangle trig used to be really common. It's kind of fallen out of favor in the last, I don't know, a few decades, 20, 30 years, and now most everything is taught from a standard position approach. Basically says that if you have an angle theta measured in standard position and you have a radius r, and you have a point somewhere on the terminal side of that angle, and the x and y coordinates of that point are known, that the 6 trigonometric ratios can be found by taking the ratio of x's and y's and r's in some combination. Now, I'm sure you've seen this before. This should not be new. Okay? So depending on where we are at when we're working on a problem, sometimes it is more acceptable to use the right triangle approach, and sometimes it's more acceptable to use the standard position approach. It's just, where are you at? What's the problem look like? How does it draw out if you were to sketch it? Which one will give you a better understanding? All right, when it comes to evaluating trigonometric functions, there are a couple different ways, basically 2 broad categories. One is to use some sort of decimal approximation in technology. Now, I use the term technology. For most of you, that means your calculator, but as you progress in your mathematical career, the calculator is going to transform into computer at some point, maybe a computer algebra system, a CAS system like Mathematica or Maple or MATLAB that you might end up using at some point. Okay? Now, the old school approach is to find exact evaluations, and we sometimes need exact using trigonometric identities and formulas from geometry. Trigonometric identities. Now, this page right here that I'm showing you right now, or this part of the page, should be nothing new. You should look at everything on here and go, yep, I've seen that before. Now, you may or may not have some of these memorized, but you definitely should not look at this and go, I've never seen that. If you've never seen this before, and you're being honest when you say you've never seen this before, you need to go back to your trigonometry teacher and tell them that they did you a disservice, because there's no way you should have gotten through trig and never seen this. Okay? I'm going to highlight some of the ones on here that we use tons of times here. We use Pythagorean identities so much. Okay? We use double angle formulas, specifically sine and cosine, sometimes tangent, but more specifically sine and cosine, quite a bit. Okay? The reciprocal identities are always being used. Okay. The reason we use the reciprocal identity so much is we have buttons on our calculator for sine, cosine, and tangent, but we don't have buttons for cosecant, secant, and cotangent. So we like to turn things into things we have buttons for. Okay. Law of cosines, law of sines, sometimes as well. Okay. If you're using technology to evaluate trigonometric functions, make sure that your calculator is in the right mode. Degree mode or radian mode. The number one question that I get from students complaining about their answer being correct and the system, the homework saying it's incorrect, is this issue right here, where they have their calculator in degree mode, they're punching in radians, and what's happening? They're getting wrong answers, but they're saying, I did it right. And, well, yeah, you might have pushed the right buttons in the right sequence, but your calculator's in the wrong mode, so you're answering in Spanish and the question is asked in English. Or vice versa. All right. Trigonometric angles, common values of trigonometric functions for common angles. Again, this should not be new. You should be looking at this going, yeah, I knew that, yeah, I knew that, yeah, I knew that, yeah, I knew that. These are the big ones that, honestly, at this point, you probably have memorized. If you don't, it'll be something that you might want to think about, because we just use them so much. I'm not going to quiz you on this in the sense of, hey, you have to know this, hey, you have to know this, hey, you have to know this. But when you're working a problem and you've got to spend 2 extra minutes figuring out the sine of pi over 6 because you don't have it memorized, all that is going to do is add 2 minutes to a problem that you don't need to add 2 minutes to. Okay? So these are just those things that you should walk into it knowing. You don't walk up to the start line of a marathon and not know how to tie your shoes, because that's just a fundamental skill that you should have already when you walk up to the start line of a marathon. We're in calculus. You should know algebra and you should know trig. I'm not expecting you to have obscure trigonometric identities memorized, but basic trig, you should know. For example, what trigonometric functions are positive and what trigonometric functions are negative in a given quadrant. If I told you that sine is positive and cosine is negative, what quadrant does that angle terminate in? What quadrant is the terminal side of that angle in? And you should be able to look at that and go, well, sine's positive in first and second, and cosine's negative in second and third, and so they're both true in quadrant number 2. It's not terribly challenging. The logic isn't hard there, but it's just some little things that we should know, some little things we should remember from trigonometry. Do you remember reference angles? Remember the idea of using reference angles to evaluate the trigonometric value of a function. So the reference angle is the positive angle made with the terminal side and either the positive or the negative x-axis. It's that little piece when you're in that second quadrant. It's the overlap when you're in the third quadrant. It's that little missing piece when you're in the fourth quadrant. And the deal is that the trig for some angle theta is either going to be the positive or negative trig of that reference angle. And the whole idea behind reference angles is if you memorize the first quadrant, you'll know all the quadrants then. If you memorize the first quadrant and you know this, reference angles say you can know all of them. Okay, all right. The video's at 21 minutes right there, so I'm going to stop and we're going to come back in video number 2 and start right here doing some trigonometric solutions. We're going to solve for trigonometric equations, solving for angles, solving for other things. Okay, all right, see you back here.